Assalamu alaikum. This is day 4 at NCP 13 Summer School on LHC Physics. Unfortunately, I don't went today due to some circumstances, road blockage issue. But for you guys, I have some recorded lectures by my friends. So stay tuned and watch.
And the ion chambers in order to have several meters of level arm. Even though sigma heat in the ion chambers is not that good as in the innermost region, and even though the magnetic field is 2000 instead of 4, we still have enough good resolution on the muon momentum at high degree, which is also computed with dedicated algorithms for fully exploit the potential of the detector. So this is very simple physics. And another thing that we can, let's say, estimate with very simple concepts is the time resolution requirement for detecting muons at length. I already mentioned that we use muons for triggering. What does it mean? It means that since muons provide interesting physics signatures, we, for different searches, for different measurements, we look for final states with 1, 2, or 3 muons with different ET thresholds or invariant mass requirements or separation requirements every 25 nanoseconds, which we call bunch crossing. And then, if you want to trigger on muons, you must associate the detected muons with the correct 25 nanosecond bunch crossing. Now, a simple exercise might be to estimate what's the worst time resolution that we can accept that is still providing a sufficient bunch crossing identification. We can assume a Gaussian distribution, and we can say if we want to associate a bunch crossing with 95% efficiency, then our time resolution must not be larger than a few sigmas. The 25 nanosecond bunch crossing must be smaller than a few, let's say 2 or 3 sigmas, depending on the efficiency we are targeting, where sigma is our time resolution. This means that we need detectors that have a time resolution well below 10 nanoseconds. So putting everything together, muons are the only particles capable to reach the muon chambers, so particle identification is, let's say, achieved combining hits in the muon chambers with the signatures in the inner tracker. And then we want to measure the muon momentum, and we need to find a trade-off between a strong magnetic field, a long level up, and a good spatial resolution. Depending on the PT of the muon, we either use the inner tracker or also use the muon chambers for the muon measurement, for the momentum measurement. Finally, muons are used for triggering, so we need to use them for collecting interesting physics events, and so we must associate them to the correct bunch crossing. This means that we need also good time resolution in the detectors. Okay, so these are, let's say, the requirements from the detector point of view. And then we can start looking at how do we, in practical, how do we put all these pieces together? So how do we connect the dots in the detector? This we call muon reconstruction. We must distinguish between local muon reconstruction and then, let's say, global. Actually, global words is also used for other stuff. But let's say local and overall muon reconstruction. Why? Well, we have different detectors with different technology. For example, we can start from the silicon tracker. Okay, local reconstruction will mean that this is the algorithm that we run every time we want to measure the track of any charged particle in the silicon tracker. The algorithm is actually computing intense and quite complex, and this is one of the things that we work a lot on for improving the performance and for finding a trade-off between computing efficiency and let's say quality of the result. The algorithm we use is the so-called combinatorial track finder, which is basically in charge of putting together the different dots in the silicon tracker. Now, the tracker in a typical proton-proton collision event will be full of hits because the density of tracks, this is so close to the proton-proton collision point that the density of tracks is really crazy. So it's not trivial to find the best combination of dots that will lead to a high quality track. How do we do it? Is that, okay, we look at all the hits and then we find some initial hits to start from, which we call seeds. Actually,
and I hope that it moves now. So it was stuck. Okay. So W is boson physics in general. All the subjects which are related to standard model, like jet, photon work, and other important subjects, are called standard. Standard model, which sounds a little bit like boring, but in fact it is not boring at all, because historically the exploring territories by
higher the luminosity, the more brilliant per second. So increase the probability of observing rare physics phenomena when you increase the luminosity. So after 1 year, the cumulative measurement of the collision rate for 300 femtometer burst path is a crucial metric for the amount, and new phase 2 trackers because right now NCP, the experimental analysis, is working on the trackers. So we are more focused on the tracker side. But the strip detector was planned to 600 femtometers. So they are sustainable approximately 600 femtometers burst bar. So design and function up to integral luminosity 600. Beyond this, radiation damage would be likely to degrade the performance. So it's detectors and as well as electronics. So we check they are survive or not after some slides. So radiation damage induced leakage current. This is normal, and the thermal runaway. Thermal runaway actually when your systems heat up and your cooling system is not properly working. So you heard compact non-solenoid, but I'm giving you some other facts that will be very useful for you guys, especially in the physics. So here you see magnets. This is very important. That's why we call the solenoid. So compact, because they are very much close to each other, and ions because they detect the ion system as well. So we have a powerful magnets. They are needed to bend the charged particles. They fly outward from the collision state. If we don't have a magnet, they can fly outward. So that's why we use the magnets. They should fly outward from the collision rate. So electricity we are using for this magnet, because this is a superconductive magnets. The superconductive magnets approximately 18,500 amperes is circulated within this valve. The superconductive magnets is ramp up and ramp down is very careful, and we should need to cool down by using the helium. So that's called the cryogenic systems. Cryogenic system cool the magnets as well. If we are not properly ramped up, they are going to quench. Quench normally we are called, they have a lot of resistance. They lose the superconductivity of magnets, and then if you are not properly ramped up, they are lost and complete system destroyed. So ramp up and ramp down, you should be careful. It's not basically it's engineering jobs. That's why you should bear some of my words. So they generate a magnetic field around the 4 Tesla, which is about 100,000 times strengthen the Earth's magnetic fields. So high magnetic field must be consigned to the volume of the detector, and is done by the straight steel loops. That's why they are too much heavy. Total weight is 14,000 tons. So if we are not putting these loops, so their magnetic field destroy outside. So what exactly the purpose for these magnets? They also identify the charge of the particles, because positively and negatively charged particles bend opposite directions and in the same magnetic field. And they are also measure the momentum of the particle and analytical magnetic field. High momentums particles bend less, So in high energy physics, we are very much interested with the high momentum particles, and as compared to the low momentum charge band flow. So I just take the slice of CMS. So here you see four basic purpose of this. This is the bending particle for the magnets. I already tell you, identify the track. We need a silicon trackers, and the measuring energy we need calorimeters, like electron calorimeters and hadron calorimeters, and detecting muons. That's why we need our protocol of muons. So I hope you understand why we need all of these detectors. And the muon chambers you see passing through the CMS bending field and both way, depends on the weather of the magnet inside and outside. They are leaving hits in the muon chamber. The muon chamber at the end we have an RPC, then we have drift tubes, and then the CSC, cathode strip chambers, and the jam. Last one is the jam, gaseous electron multiplier chambers. So fortunately, Pakistan and experimental analysis, our teams were two of them, not two, but gaseous muon detectors. We work for RPC, resistive plate chamber, and the gaseous electron multiplier detectors. So this is the last one. They give the trigger as well, and the RPC is a resistive plate chambers. Is made with the bakelite, but you can make with the glass as well. And we use the gas mixture for the argon carbon dioxide and isobutane for the quenching purpose. And this is a fast gas ionization process inside. Because the heart of this RPC we have in a bakelite. Bakelite like a gaps. We have a gaps, and top and bottom we have using the bakelite with we have using some spacer and flush the gases inside, and on the top of this we putting some graphite coating and high potentials. So in this case we have a noble gases inside. When any charged particle comes, they are ionized, and we put strips, like strip number. So charge automatically deposit on the strips, and we collect the charge from. This is normally used for. This reactors normally is the timing for CNS. The next
coming justify the different predictions coming from the theory and the experiment under the window of the Hammad physics rather than any other branch of the particle physics. So the main motivation to choose the heavy ion physics because it offers you to understand the nature of the confinement, means how the hadrons are combined,